Hi, my name is Shawn Donnelly. I'm the Deputy Program Manager for the NASA TROPICS mission, and I work at MN2 Lincoln Laboratory. So today you're going to hear about the low latency data demonstration from the Pathfinder satellite. So before I get into the results from the Pathfinder demonstration, I want to give a little background on the TROPICS mission as well as Pathfinder for those of you who are not familiar with TROPICS. So TROPICS stands for the Time-Resolved Observations of Precipitation Structure and Storm Intensity with a Constellation of Smallsats. You can see I had to look at the screen to read that because I can't remember that acronym for the life of me. It's been 6 years in the program and I still can't remember it. But TROPICS is a NASA Earth Venture Instrument Program led by the principal investigator of Dr. Bill Blackwell. And TROPICS provides an innovative solution to provide data for severe storm intensity forecasts, producing temperature products, water vapor, precipitation, and cloud properties. Now we do this in a sort of in a new way. We're building a constellation of 3U CubeSats. And for those of you who are not familiar with CubeSats, they're very small. One U of a CubeSat is 10 centimeters by 10 centimeters by 10 centimeters. So altogether, a 3U CubeSat is about the size of a loaf of bread. Blue Canyon Technologies is providing the 2U spacecraft for our CubeSat, and us at Lincoln Laboratory are built the 1U multi-channel passive microwave radiometer. And the result of this constellation is a better than 60-minute median revisit rate of anywhere within our orbit. So you'll see the number 6 on there for 6 satellites. That is the number we had built for the program, but unfortunately about 2 weeks ago we launched the first 2 satellites that failed to make it to orbit. So we're now down to 4 satellites, sadly, but those 4 satellites will still be able to make that 60-minute median revisit requirements that we have for the program. And listed below, we have our mission partners for the ground segment. We are using KSAT as our ground station network. Blue Canyon is also our mission operations provider. They built our bus, but they also provide mission operation services for us. And us at Lincoln Laboratory, we're the Science and Payload Operations Center. And like just mentioned, UW here is providing the data processing center for the program. And over here to the right, that's just an image of our radiometer. It's actually about the size of a coffee cup, so it's pretty small. And here's an image, a global mosaic from our Pathfinder satellite that's currently in orbit. This image over to the left depicts our 1 ground station. So currently, TROPICS has 1 ground station dedicated for the mission. We're in the process of adding more, and obviously that is a key driver for the latency of the TROPICS mission. So I mentioned median revisit rate of better than an hour. So how do we achieve that? Back at the inception of the TROPICS mission, we did an exhaustive study to determine what is the optimum configuration for 6 satellites to get this median revisit rate time. And this is the configuration we came up with. It's an altitude of 550 kilometers, 3 different orbital planes separated by 120 degrees in right ascension, and 2 satellites per plane at about a 30-degree inclined orbit. And here's just sort of the result of what you see where most of the tropical storms occur, and where our median revisit rate time ends up being around 43 minutes. That 43-minute number, again, is for 6 satellites. For the 4-satellite constellation, it's roughly about 55, 57 minutes. Still better than the 60-minute median revisit rate time. The 4-satellite constellation, we're going to, instead of have 3 orbital planes, we'll back it down to 2 orbital planes and likely separate them by 180 degrees as opposed to 120 degrees. Our payload runs at about a 24/7, should be 24/7 duty cycle nominally. The CONOPS for TROPICS is purely just to downlink all of our science data. We don't have it. We have no latency requirements. It's a science mission. So the base requirement is just get all the data down, and the result of that is a an average of 3 downlinks per day. And that's purely because we pay per contact and we need to get all the data down, and that's how many we need just to get all of our data. So, and like I said, Hartebistuk, South Africa, is our one ground station, and we are in the process of adding more. So for TROPICS main mission, the nominal latency will roughly be around 4 hours. So a little more information about our payload. Like I said, the payload's a 1U microwave radiometer with 12 channels, G, W, and F band, and it's a 30 RPM spinning payload. And I have a video here that will show the that's the satellite simulation of the satellite flying in orbit. And that red line, the red area, is where the payload is sampling the ground. So the satellite flies along the velocity vector and sweeping. Let me see if I can go back to it a little bit here. There it is. Oh. So there's a satellite, and as the satellite is flying along, it's slowly rolling and articulating the solar array for maximum charge of the battery. And the payload is spinning at, like I said, about half a hertz, sampling the ground at once every 2 seconds. And it collects about 81 spots in the ground, and each spot is about 8 milliseconds. And it keeps sampling the sky as well. What we sample the sky for is there are 2 sections of the sky we care about. One dark sky with outer noise calibration diode on, and one with it on. So there are 2 sections that we actually care about the data. That's shown here in yellow. And then we downlink all the spots in the ground. So our flight software throws out all the additional data that we don't need to minimize how much data we transmit to the ground. I think that's the rest of that video covers. Okay, so that's sort of a summary of TROPICS. So we completed our space vehicle build back in 2020. We completed all 6 of them, and subsequently we put them in storage so that NASA could go out and find us a launch services provider. We have a unique orbit. A 30-degree inclined orbit is not a normal orbit for launch services providers to insert us into. Not only do we have a unique orbit, but we also have a requirement to be the prime customer driving the schedule. For us to get into the right ascensions that we need to be launched into, we have a strict timing requirement. So we need priority, and we need a unique orbit. It's hard to find launch providers that can get us where we need to be. So they were put into storage, but we had a 7th satellite, which was our engineering design unit, and we thought it would be prudent to get that up to flight quality and launch that on a rideshare, just as a risk mitigation exercise. So we did that. So last summer, we launched the TROPICS Pathfinder, and we didn't launch it to 30-degree inclined orbit. It was a risk mitigator. We really wanted it to work on calibration algorithms, test flight software, just validate it works. It was our first time launching this in orbit. We really wanted to get something out ahead of time just to kind of work with the data. And fortunately we did. We learned many, many lessons. We couldn't imagine trying to commission and work with 6 of these all at once. This was a much larger effort than we expected, so we're very happy we did it. And we got some great data from it. You can see here's an image from Typhoon Mindel, image from the TROPICS Pathfinder using the 205 gigahertz channel. So for TROPICS Pathfinder, we had 1 ground station up in Svalbard, which is obviously pretty optimal for a polar orbit. I'm afraid to touch this laptop and have the screen go away. Okay, so since we had a satellite in orbit, NOAA had contacted us to do a low latency demonstration. The satellite is mostly identical to what's in orbit, what will be in orbit for TROPICS, and the ground segment is mostly the same. So it would be almost an apples to apples to see what kind of latency we could drive the Pathfinder down to. Like I said, with TROPICS, we have no latency requirement. Pathfinder is the same, and the nominal latency for Pathfinder, again, ends up being 4 hours because all we need is 3 contacts per day. We just spread those out during the day, and that's kind of what we come up with. So for the low latency demo, Noah basically said, let's see how fast you can go, and that was our objective. Additionally, any software tools, methods that we learned and applied during this demonstration, we wanted to make sure it was forward compatible with TROPICS in mind, so that we could apply what we learned directly to the constellation once we launch it. So these are our mission operation partners. I had mentioned before that Svalbard was our only ground station. For this demo, we enabled another ground station in Punta Arenas down in South America to try to increase the number of contacts we could get, which I must say was a very seamless addition with KSAT. Everything is software configuration backend from their network to their RF equipment. It was a simple addition just to add Punta Arenas for this demonstration. Blue Canyon, like I said, is our mission ops provider. They do all the scheduling, command and control, and pulling out the level 0 data of our satellite stream. And Blue Canyon uses EC2, and they got Russ's attention over there. So they have virtual machines for each that talk to each satellite, and they take that and extract our level 0 data and put it on S3 for us at Lincoln Laboratory to pull, but also the University of Wisconsin to do the data processing. So I put this latency definition chart in here because anyone I talk to, which is most people not outside this room, don't have trouble conceptualizing what latency means. So this is probably unnecessary, but I'll go through it anyways. So what we are considering latency is the age of the science data once it's processed at the level 1. So this demonstration only went out to level 1. Level 2 products weren't quite ready for a low latency type experiment. So the data that is being acquired, so the latency that we're really computing here is from the end of the loss of signal at the prior contact to the loss of signal at the current contact, and the average time of that duration plus any of the processing time that is incurred at Blue Canyon and at Wisconsin. And I'll say that if you guys saw that video earlier of the satellite flying along the velocity vector, when we have contacts, we pitch our spacecraft to point at our ground station, so our radiometer is then kind of spinning around and not pointing towards the Earth. So the data that is acquired during a contact, I'm running out of time, during the contact is not usable. So here's just an example of what, from our latency demo, we have over here in the lowest latency case is 28 minutes. And this is where we had the advantage of communicating in Svalbard, and then directly after communicating in Punta Arenas. That is a pretty short duration for us, 28 minutes. We took the average time, which is right in the center here. That average time plus processing is where we got our 28 minutes. The longest latency case is about 140 minutes. Most passes we have the ability to communicate in Svalbard, but some passes are really low elevation, and it made the data, made the contacts not really usable. So some cases ended up being a bit longer. So the result of the 5-day demo was an average latency time of 55 minutes across an entire week. And that's strictly driven by ground station location and availability. And that's really, it's pretty simple with LEO satellites that is the case. So when we had the opportunity to communicate in Svalbard and in Punta Arenas, that's the green bar down here of all those contacts, the latency that's in the 40-minute range. If we had subsequent passes in Svalbard, we landed in about the hour time frame. Then up in the purples when we had passes, multiple passes in Svalbard, but we could not communicate. So what does that mean for the constellation? That's really why we did this. So we applied what we learned there and added it did a simulation for the TROPICS constellation. And these are the ground stations that I said we will be adding. Right now we have Hartobishtuk, and we're adding Los Angeles, Portillano, Singapore, and West Australia. And the main driver with those is getting IT licensing, which is a timely process and one that's kind of sort of out of our control, but they should be by the end of 2022 for most of them. And Singapore, the holdup there is just building the ground station with KSAT. So 45 minutes is the latency that we computed. And really, I focused in on this analysis on the latency from the Atlantic Basin. Because if you take a global average, it's sometimes misleading what your latency can be. And a perfect case is the Indian Ocean, is you cross from one ground station to another, your latency there might be exceptionally short, but in the Pacific Ocean it might be much longer. So to sort of bound this and define a location and how long you have to wait, I use the Atlantic Ocean, and the Atlantic on average is about 45 minutes. And there are a lot of times it's much shorter. You can see this orbit here where we sweep through the Atlantic and right to Hartobishtuk. It's optimal, but there are times where we have the ability to snake right through this region and not hit any ground station, and the latencies are much, much longer there. So ironically, I did the same simulation globally, and it was also a 45-minute latency. So the global latency that you'll wait for data is about 45 minutes, which is the same as the tropics, but the Atlantic Ocean. But the Atlantic is much more specific and guaranteed. So, in summary, the NOAA exercise showed that the Pathfinder satellite can achieve a sub 60-minute average latency, and if you propagate that out to tropics, we expect about a 45-minute latency. The level 2 products are in the process of being matured to move a little faster, so that those can be included for tropics by the time we get in orbit. And finally, we're very excited because we feel that the TROPICS constellation provides a unique revisit rate over the tropical regions, and combine that with a low latency effort, we hope there are some applications that could really benefit from that. So that's all I have.
Thank you very much, Shawn. We have time for questions. Thank you, Jenny.
Thank you so much. It's good to see a new kind of technology used for this observing the high camera resolution, especially in the hurricane severe weather area. So my question to you, you mentioned about air quality. What kind of sensitivity of your microwave measurement provide any reliable high-performance air quality products?
So we are roughly, so I don't have all the numbers because we have 12 channels, but I think we're averaging around a 1 Kelvin accuracy, sub 1 Kelvin for most channels. Was that your question?
No, we want to provide air quality measurements, air quality signature, pollutions and other stuff. How would we able to do that kind of information?
Oh, how would it? I would have to defer that to the science team members. I'm an operations guy, so I would have to defer that to my boss, Bill. Yes. Okay.